Afternoon, everyone. Welcome back from lunch, and welcome to a discussion on whether the premium risk standard formula fits well or not well, and how you could tell. I debated whether to lie and say there'd be no formulas in the presentation, and then you just sort of realize as I got on that I was lying. There are some, but for the most part, you can ignore them if you want to. You can still follow the narrative and the story as we go along. As usual with my presentations, this reflects the topic that I've had an interest in and I wanted to learn a little bit more about. And so I guess I will take you along the journey I've been on. And hopefully it's not all absolutely obvious and trivial to everybody, but hopefully it's also all pretty understandable and you can follow the journey. Now, you're here, so maybe I don't need to do the full sales pitch around why you should be here, but I'll do it brief one anyway. So from an insurer's perspective, or an actuary's working for an insurer's perspective, if you are doing things like capital allocation, or you're using capital in your reinsurance decisions, or in fact in your pricing, and if you're not, maybe you should be, but if you are doing those things, you're very likely heavily leveraging the standard formula, right? Many of us do that. We haven't necessarily done all that detailed work, so we take this existing standard formula, those existing processes, and reuse it in other ways. So then you might really want to make sure that you've got the best handle on those calibrations and how well the model fits. I know many of us, certainly for the liability for remaining coverage, where we do need to calculate a risk adjustment, again, we lean fairly heavily on the standard formula. So if you have any linkages there, you may want to be more confident about that. And for the reviewers, for the auditors around, if you're trying to get comfortable with things, maybe I'll give you some ideas of ways to kick the tires and check and be comfortable that these standard formula-based approaches are workable or not. Same thing for earnings risk accuracy. But really, the last one here, and I don't want it to be the most important one, but GOR 3.1 really does actually require us to assess the appropriateness of the standard formula. When we use the standard formula in our ORSAs, we have to say why we're doing that rather than some fancy, more involved economic capital model. And in South Africa, those practices are pretty poor. I'm involved with a few European and UK insurers, and the extensive work that they go through, mostly every 3 years, but also a little bit of work every year, to check whether the standard formula is appropriate or not, is just vastly more than what we're doing here. So I think we probably should be doing more, and at some stage the regulator may decide to push a little bit more firmly on that as well. Speaking of the regulators, if they want to ensure that we are all holding enough capital, they also might want to have a better view on where their standard formula falls down and where it doesn't. I mentioned the ORSA and the need to demonstrate there that the standard formula is appropriate. Well, the regulator should also have some ideas on whether what we are doing there is good enough or not. Although insurer-specific parameters, or in Europe called undertaking-specific parameters or partial internal models, aren't very common, if you are looking to approve one, you should probably have some ideas of what things to look out for. And risk-based capital is growing widely in our continent, and as regulators are looking to impose new risk-based capital requirements, the only work they're going to have to do to either assess those calibrations or determine those calibrations, or decide when to allow insurers to do their own. It would be helpful to understand these things a little bit longer. Now, you might be asking yourself why premium risk, of all the more interesting, more exciting components of the standard formula, why did I pick premium risk? Well, it's really by a matter of exclusion. Operational risk is hard, let's call it maybe impossible to really accurately assess. We can tell because the banks have generally pulled back from having operational risk assessment, certainly for regulatory-based approaches. There are things that you can do there. They can be interesting, they can be informative as a process, but I don't know how excited I get about that final overall answer on operational risk. Market risk, there's lots to be done on market risk. Last year I did a little bit of work on equity risk, and there's plenty of things that can be done generally speaking around market risk, but it's not insurer specific, so that's why this really isn't the topic of today's discussion. Intangibles, a bit of a pet peeve for me. You shouldn't have intangibles anyway. If you think you do, come, we can fight about it later on, but there really shouldn't be any intangibles, and therefore you shouldn't be worried about the stresses or shocks to intangibles. Cat risk, very important, very exciting, way more complex to do, probably beyond, sort of 50 or so of the 55 odd insurers in South Africa to do much on that. And unless you're calibrating your reinsurance program to be just at the SAM 1 and 200 level, it probably isn't going to make that much of a difference to your net capital requirement after you've taken reinsurance into account. So the reason why premium risk is, well, these ones don't seem to be particularly exciting. Let's look at premium risk maybe that'll be a little bit easier or more useful. I'm going to guess most of you understand, it's probably worth explaining the mushrooms. So mushrooms is a small fruiting body on top of the soil, and you can have these mycelium networks for like kilometers underneath it. So this is me not having mind, or maybe that would be a good idea, but not having mind-altering mushrooms, but this idea that we see small things on top, and as you delve down, there's a little bit more complexity underneath, so that's why mushrooms. So a very brief refresher on premium risk. For those of you who recognize this formula, I'm a bit concerned because it's a very stylized half approach. This is not actually the standard formula. For those of you who wanted to tell me this is not the standard formula, I know. It is still a stylized, helpful, useful, broad measure of where the capital would come from for premium risk. You take 3, the magic number 3, multiply it by the standard deviation for that line of business, multiply it by the premium volumes, and that gives you the capital requirement for that particular subset of capital. You can just reassess that to not a real term, a standardized VAR, but just if we can scale everything by premiums, we get capital over premiums, so we can sort of forget about premiums and premium volumes for the rest of the presentation. And this is really a function of 3 and the standard deviation. Now, if you read the footnote in FSI 4.3, it says that we choose 3 because it is a rounded version of the 99.5th percentile from the standard normal distribution, which is interesting because all of Solvency II says it's from log normal. I don't know where that normal footnote came in there, but as you'll see, normal doesn't really fly. Also interesting, in the Solvency II specs, they talk about having to demonstrate for your USP application that both loss ratios and standard deviations are proportionate to premiums, whereas the standard rules talk about variance, not standard deviation, being proportionate to premiums. So definitely there are some gremlins buried in the FSIs there, which does make me wonder how strictly those are applied when we are looking to apply for a ISP. Okay, so we have 3 times sigma or standard deviation. And one key question is, well, what should sigma be and what affects it? And the other is, well, what affects the number 3? Why is the 3 there and what affects that? The standardized VAR over sigma, the only reason I'm putting that up there is I'm going to be showing that sort of result for a few different models at various times. Is this bigger or smaller than 3? And basically, if the model suggests it's bigger than 3, probably the standard formula isn't fitting very well. If it's less than 3, you're good to go. And please, it is standardized VAR. It's just to show that this is scaled by premiums. Right. So the next couple of slides, I'm going to talk to some of the hypotheses, effectively, that I had about likely areas where the standard formula would fall down. The beautiful 3 in glowing lights there is because I initially thought that there probably would be more around 3 than some other elements. Spoiler alert, 3 can be problematic, but it may not be as big a culprit as I'd initially suspected. So the first thing is, well, do smaller portfolios have higher volatility? And we'll touch on that in a moment, but hopefully that's a relatively straightforward sort of idea. And clearly no part of the standard formula directly addresses portfolio size in the capital calculation. Second point, a little bit more subtle, does portfolio heterogeneity, where maybe just the sums insured are a little bit different from one another. If you have higher variability in sums insured, will they give us a higher standard deviation or higher value at risk over standard deviation? We can check that and see. And then there's slight confusion around log normal versus normal. What are, in fact, the distributional assumptions that we would expect? What we see in practice, what we need to demonstrate, and what is the relationship between value at risk and standard deviation? Frankly, is 3 enough? Especially when you look at proportional reinsurance, it's relatively unexciting in terms of decreasing your risk. We'll show a quota share result, but really my question was whether would surplus have a meaningful impact on the variability within the portfolio, particularly, or maybe obviously, when you have different sums insured within the portfolio. If the sums insured are all the same, it's not going to be a particularly exciting result. So we're going to look at what impact surplus reinsurance has. And we look at that, we can also think about, well, how much surplus was embedded in the calibration data, how much surplus was embedded in your past and in your future, how much impact is that, do we need to worry about that? And then what started my whole thinking around this was, well, surely there's more opportunity for insurers to use insurer-specific parameters to be more efficient, to be more capital efficient, to decrease their capital requirements. And isn't it a shame that in South Africa, we only get to use 50% of our own data, even though we have 10 years of high-quality data, to set the new volatility factor. So we're going to talk a little bit more on that and understand, is that enough, is it too much? Point 6 and 7, I would love to include in the presentation. For a while, the slide deck was 60 slides long. It's not quite that long anymore. But there are some interesting points here as well around how we aggregate risk within the standard formula. Lots of assumptions around Euclidean, elliptical methods or elliptical distributions, and Euclidean approaches which are probably approximate. And similarly, the idea that for a monoline insurer, many of these potential concerns are actually a much bigger deal than for a diversified insurer. At least we're looking at your total capital calculation. As soon as you are looking to do capital allocation or pricing, actually then with your monoline or diversified matters a little bit less. But 6 and 7 we won't be covering today. Now, I'm going to touch on idiosyncratic risk models, not because they are an appropriate model, just to sort of maybe wean you off that idea and to demonstrate the impact. So here we have a model, a very simple model. You may have studied a model like this. We're modeling individual claims with a Poisson frequency and a log normal severity, targeting a loss ratio of 65%. And what should be fairly obvious is that the standard deviation of the loss ratio declines at a square root nature over the portfolio size. So clearly, for a very, very small portfolio, this is all going to be about process risk or statistical fluctuation risk or idiosyncratic risk, and it's going to be very, very high. But for larger portfolios, 50,000, 100,000 policies, hopefully it feels also way too low. Now, this is not the sort of standard deviation we expect to get for a portfolio. And for the simple reason is, actually, for large portfolios, the risk we're exposed to isn't typically statistical fluctuation risk, or at least not mostly. It is the more systematic components. So, big reminder, we need to be looking at systemic components rather than the idiosyncratic pieces. I'm not going to go through each of these items. Hopefully you're relatively familiar with them. But the thing is, it can give rise to systemic risk. It could be parameter risk, or model risk, or structural risk, or systematic risk, or cyclical risks. And many of these terms are either synonyms or they're fuzzy terms for the same sorts of things. But some examples might be where you just don't have a solid estimate for the actual parameter. The parameter, be it the overall frequency or severity, is uncertain and changing over time. It could be changing over time due to trends. It could be changing over time due to seasonality, could be due to climate change. Any of those different matters could make that change, and therefore you're not going to get that beautiful decrease by the square root of n of your portfolio. A slightly different form of systematic risk is where your model itself isn't working correctly. You've maybe underestimated the tail risk, maybe due to the way you've aggregated risks and so on, or you've lost some independence term. That means you're also not just having this statistical fluctuation, there's going to be more going on. Maybe the biggest items, ones we might be most familiar with, are the structural items. I don't do any modeling on the underwriting cycle, even though it's possibly the more important one. But if you have an underwriting cycle, that is going to be driving your loss ratios from one year to the next, whether or not there's statistical fluctuation, because some years you're going to have good results, some years you're going to have bad results. And we all know in theory we should ignore the underwriting cycle, and then in practice we can't. Inflation, and in South Africa's case also perhaps foreign exchange, can be a big driver of claim experience from one year to the next. Inflation itself is a time series process, will give rise to some time series effects, but it will also mean that the fluctuation from one period to the next won't just be about statistical fluctuation risk. Shifts in claims handling and regulated environments also can have an impact, and I've already discussed seasonality and macro linkages, where what's happening in the broader economy can flow through into what's happening in our own claims experience. So again, a little bit of a sales pitch, but hopefully you understand, yes, there are non-idiosyncratic factors that we need to get a handle on. Right, mostly an introduction done. Let's talk about the actual models I'm going to be exploring with you. And the good news for you is that this was hard work for me, and you shouldn't have to need to do this, because what I'm trying to do is trying to create artificial portfolios to be able to test. Whereas you, if you need to do this, you'll probably have your own portfolios. So all the hard work about trying to create these and simulate these and try to get the pricing to be vaguely sensible and calibrate them all, which was a lot of fun, you shouldn't need to worry about. But I'm going to talk you through the basic models that I looked at. They're not the only models you could look at, but they demonstrate some of the impacts. So the core structure across all models is that we have a base frequency. I chose 10% for arbitrary reasons, and the severity is log normal. You could have chosen gamma or something else. You're not going to get fundamentally different results. I chose a coefficient of variation parameter there to try to get some reasonably plausible claims variability. But then I did have to cap the claims at 100% of some insured, which is very, very sad. Because when you have a cap in there, it means a lot of the algebraic ways to calibrate your models fall apart. You need to end up in the world of simulation which is quite painful. The premiums are deterministic premiums. I mentioned I didn't, in the end, include any underwriting cycle in those premiums. And that's been calibrated to a premium rate, theta 0 times the sum insured, to target the loss ratio that we are looking for. There are 4 versions of these models that I looked at. The first version you've already seen, and we won't look at it again. That's purely idiosyncratic risk. Version 2, we add in some systemic frequency risk. Version 3, systematic severity without the systemic frequency. And version 4, we combine those with a bit of a correlation between frequency and severity as well. Excuse me. I'm not going to go through each of these in detail, but you can see here for frequency, we just add in a systematic component. And the second term there, the beta squared term, is just to adjust it so we get back to the same mean that we're looking for. It helps with the calibration. Nothing else really is different. So there's a perturbation within the portfolio for each time period. So the parameter is not constant, it's varying, and therefore that affects all the policies and all the claims. Version 3, we revert to constant frequency. Now severity has the same systematic component, also with a normal perturbation, and premiums are still constant. Version 4, the same for the frequency and severity, but we just add in a 50% completely arbitrary correlation between frequency and severity. I'm not going to be spending too much time on version 4, mostly because the calibration hasn't worked perfectly. There are 1 or 2 results there, but we're going to focus on version 2 and version 3 in the presentation. Now, those are the models, the key portfolios, or the features of the portfolio. We're going to have a homogeneous portfolio with the exact same sum insured across all policies, and then one where I've added some artificial heterogeneity. I've assumed a log normal distribution of sums insured. That's not particularly important, just we have a range of sums insured there. A log normal does give you some pretty hefty tails, so you get quite a broad size of claim sizes there. I modeled no reinsurance and quota share, which is not particularly exciting, and then surplus. I target 2 loss ratios, 65% and 25%. 65% is maybe a little bit on the higher side for many portfolios. 25% just shows you maybe a VAPS portfolio. Would be some other portfolios with loss ratios in that sort of range. You can see what that does. Turns out loss ratios are maybe at least as important as standard deviation. I targeted a standard deviation of 10% where possible. As I said, some of the calibrations struggled a little bit. That really is a benchmark that we are aiming for. Now, to get the calibration working correctly, I didn't want there to be any sample error in the calibration, so I was trying to simulate large portfolios with large simulations of those. So between 100,000 and 1 million simulations, with using more simulations for the smaller portfolios where there's obviously going to be more statistical fluctuation. Some of those did fall over and didn't come back to life, so we didn't have all of those combinations. The sort of outputs that I'm looking at the value at risk over standard deviation, that number to compare to 3. The value at risk over premiums, so the overall capital intensity of the business, standard deviation, and a few other measures that we will take a look at. This slide could be a bit longer. These are some of the core limitations, and I will spend a little bit of time on each of these before we start looking at results. So I'm ignoring reserve risk, but I'm ignoring reserve risk in a number of different ways. So non-life underwriting risk, as you probably know, comprises both premium risk and reserve risk. And in fact, when you combine these two with imperfect correlation, you're probably going to slightly moderate the results, right? The end results could look a little bit more normal, and therefore the 3 factors probably going to be a little bit closer to reality. So that's an important one. But also, I'm effectively modeling these loss ratios as ultimate loss ratios. I'm not even talking about whether these are paid or incurred. This is just the overall loss ratio, being a little bit vague around what happens on the reserving side. And this is important because there's an important link here. Strictly speaking, we should be looking at the 1-year loss ratio after the accident with an estimate of the OCR and IBNR at the end of that 1-year period. So if you have a reserving method which is going to stabilize your loss ratios, like a loss ratio method, that will tend to decrease the standard deviation that we see looking at loss ratios. If you have something that is a little bit more hypersensitive, like a basic chain ladder, purely based on the data, you might get a slightly overreactive measure. You might be elevating the standard deviation that you're observing from the claims here. So ignoring reserve risk here is a fairly significant simplification. There are definitely things to think about there. But again, because I'm creating simulated data, trying to go back and simulate what would somebody have been doing in each of those cases was an additional level of complexity. I'm also ignoring expenses, but I'm less bothered by that. In fact, the FSR say don't worry about the expenses when you are looking at these various parameters. My understanding is the same thing is broadly true in Europe. And I'm only assuming log normal. Not only as in just log normal, because log normal can be pretty severe, but I haven't looked at the different forms of severity. I don't think the results will be meaningfully different, but happy to have a discussion on that if you've got a different take. And then, as I mentioned up front, I'm only looking at a single line of business. And so for all these areas, the results might not look quite as normal as you might like. Adding more lines of business is going to make it look more normal and less extreme. So again, where I start saying, there might be a problem here or there, remember that's going to be slightly elevated, relevant for a single line, and slightly muted when you look at a diverse book of business. And as I already highlighted, some of the calibrations were imperfect. Unfortunately, there's lots of 8 and 10 hour runtimes. So when I realized that some of the outputs weren't looking quite intuitive, I delved back into the calibration testing. I did see there were some gremlins there. So 1 or 2 of the results are missing, and 1 or 2 I'm going to flag need to just be a little bit suspicious of. And again, version 4 in particular struggled quite a lot. Okay, back to the list of items of hypotheses. I'm first going to look at the impact of portfolio size and portfolio heterogeneity. So the blue line shows the heterogeneous portfolio. This one's where the sums insured vary, and the red line is where they're all exactly the same. So what you can clearly see is, yes, not particularly surprising, where we've got variability, an additional source of variability from the sums insured, we're going to get higher standard deviation as measured. So that's what's on the y-axis, the standard deviation, and on the horizontal axis, we have the portfolio size. But the differences aren't all that dramatic, and by the time we have a portfolio of about 10,000 policies, the differences are relatively modest. So if you do have a particularly small portfolio, you should probably be worried about both portfolio size. You probably are going to have qualitative reasons to believe you have a higher standard deviation than the overall industry-wide calibration. And if you have a heterogeneous portfolio, which most of us do, that risk is going to be amplified. However, if you go above 10,000, maybe not such a big deal. Now, for many of us, at least some of our lines of business will be above 10,000. Therefore, there's something you can maybe put to one side. But if you do have a niche line of business, a smaller line of business with fewer than 10,000 policies, this is something to think about. And again, I'm repeating myself, but for your total overall capital, maybe that major motor or property line of business swamps everything. But if you are looking at pricing or looking at reinsurance optimization or allocations, those niche lines with smaller volumes of policies may still require some love and care. This is a similar message with a slightly different vertical axis. This looks at just at the percentage increase in the standard deviation from moving from a homogeneous to a heterogeneous portfolio. So again, pretty marked of the small policy size. By the time we're at 10,000 policies, that's about a 3% increase in the standard deviation. There are so many more things that can give rise to more than 3% increase there. Really, from that point onwards, I wouldn't be that worried about it. You'll see some missing points on these lines. These are calibrations that failed. I managed to remove them. But you can see we're getting, this is the change in the value at risk over the standard deviation as we increase the portfolio size. So again, for V3 and V4 models, there is still this impact where the multiple of standard deviation for capital increases for small portfolios. Okay, impact of surplus reinsurance. This is a similar graph that you saw before, and you can see there's a dotted red line showing the quota share over the blue baseline. Surprise, surprise, if you're going to share premiums and claims in equal proportion, there's going to be no change in the net or retained result there. But when you do add in surplus reinsurance, it's going to give us a bigger benefit there. Again, there shouldn't be a surprise, but it's just worth keeping that in mind. And one of the questions here is, well, what data was used in the calibration? If there was a lot of surplus used in that particular period, and now you don't have any surplus, that is another qualitative reason to believe that perhaps your standard deviations might be higher than an industry average. But also for your own portfolio, if you're looking at estimating your own parameters and you had 8 years with a significant surplus in place, you now can that, you no longer believe it's bang for buck, you now have only quota share or only non-prop, you need to be careful. You might want to go back and actually re-estimate the standard deviation parameters from gross results rather than net. I'm trying to recall anywhere where I said we are focusing on attritional claims only here. That is embedded within the premium volatility risk piece, but it's very important. We're only looking at attritional claims, and hence the allowance for proportional reinsurance here is proportional. Okay, now I've looked at the UK form that you need to fill in, where you want to apply to take on undertaking specific parameters. And there's a lot of detail there around your data and your governance and your stability and demonstrating that you know, yes, your distribution is definitely log normal. Tricky thing to do with just 10 years of data, we'll come back to that, but you are required to show that that's the case and that the losses are proportional to premiums and the standard deviation is proportional to premiums. Again, difficult things with just 10 years of data. So I thought, well, let's see what sorts of results are coming out of the theoretical claims level models that are put together. And so version 2 says we can say, well, maybe these are log normal type distributions. This isn't particularly unexpected. We can usually get a form of log norm out of these models. I'm a little bit surprised that adding in severity actually said that the results was normal. You'll notice there's a big missing gap there on the V4 results. I wasn't happy with the calibration results there, so I'm not prepared to. It showed that none of these were fit at all, but I still have a suspicion we might get a log normal to fit reasonably well if the calibration had worked correctly. So this is possible, though, because I had huge numbers of simulations and huge numbers of data, and so I was able to get these strong tests. Again, if you've only got 10 years of data, good luck trying to get something that really gives you much of a confident response. Okay, now what occurred to me as a start to be the biggest concern would be, when is this factor 3 really going to be appropriate? And it turns out, with the base parameters of a loss ratio of 65% and standard deviation of 10%, for most portfolio sizes, we're actually looking pretty good. So most of these are below the 3 cutoff points. At a 100 policy level, hopefully nobody expects the 100 policy portfolio to have reasonable tails. That is higher. But for the rest of them, we actually are thereabouts or slightly below 3. We are above the normal assumption, the 2.5 beta, whatever it is. So we shouldn't think that there's some extra margin within the standard formula. No, we're basically at the standard formula. And you can see relatively similar results over the 3 models, and not much of an impact on the value at risk over standard deviation as you move across portfolio sizes. Slightly different way of looking at this, now looking at the value at risk over standard deviation and the standard deviation on the right-hand side. And this is one of the areas where I started to get a little bit worried that we didn't manage to get the calibration of that 10% standard deviation exactly right. It's pretty close, but ideally it would have been a little bit better. Okay, now we looked at what happens if we decrease the loss ratio from 65 to 25 while keeping the 10% standard deviation the same. So what happens here is we're going to significantly increase the coefficient of variation, and this is when problems start to arise. This is just the V2 model. It's the one that is most reliable. And as soon as you move to a higher coefficient of variation, we're now bumping fairly well through the 3 multiplier. So it turns out that it is less about having the standard deviation be reasonable and far more about having your coefficient of variation be appropriate. If your coefficient of variation is high, that 3 multiple is not going to be appropriate. But in your application to the regulator around choosing your new lower capital efficient standard deviation, there's no mention of looking at the coefficient of variation. So in your own purposes at least, when you aren't applying to a regulator, and maybe when you are, make sure you're looking at both the standard deviation and the coefficient of variation, because that will drive really whether the standard formula is at all appropriate or not. So this for me is one of the key lessons coming out of this. Slightly sadly for me, this was one of the very first charts I created about sort of 4 months ago, and it is possibly maybe the most important one. This assumes, this doesn't model from ground up, this assumes an overall log normal distribution for your aggregate claims distribution. And say, well, given a particular loss ratio and a particular standard deviation, where do you fall within this shading? If you happen to fall within the green triangle, good news, you are at or below a 3 multiple of value risk over standard deviation. Therefore, the standard formula is a reasonable fit. So if your standard deviation is close to the premium volatility factors or below, and your mean and standard deviation are within that space, you're good to go. But I can think of a lot of portfolios with either higher standard deviations or lower means that you're putting in the yellow or the red or the black areas, where you can have a much, much higher multiple than is required by the standard formula. So actually skip the millions and billions of simulations, skip all the hard work, look at this, pick where your mean and your standard deviation is. They'll give you a pretty quick view around whether the standard formula is giving you an understatement or an overstatement of capital. And you can think about, I don't know exactly where the green would move to sort of well less than 3, But it's actually quite hard to have a number that is dramatically less than 3, and quite easy to get into 3.3 up into 3.6, which is a fairly big difference. Okay, now I started this by thinking there's got to be scope to use more insurer-specific parameters. And then as I saw my own calibration efforts struggling to get to converged results, and thinking about how little data 10 years really is, I started asking the question, is 10 years really enough to determine the capital? So as you will probably remember, Solvency II gives you full credibility once you have 10 years of good quality, well-governed, stable data. You're allowed to pull out little bits and explain why you've adjusted this here and there and so on. But you can get 10 years of data and you're then fully on your own internal data. Now, those of you who have a Bayesian slant to you, you could think of this as saying we have effectively a vague prior at that point, that there's no value, no information from the multi-year, multi-insurer calibrated data. We're all dependent on your own data. Now, of course, your specific insurer experience is better than industry data because it reflects your specific business, but it feels quite a strong thing to throw out all of information. Sam did a more conservative thing, saying you only get credit for 50%. You get your full 10 years of data, and the best you could do is a weighted 50-50 between the standard factors and your own factors. So what this does is it makes it slightly less attractive to go through this whole process, because the actual upside is rather more limited, so that's fair. It's also, I guess, saying that when you have the 10 years of data, the Bayesian weight or the credibility of your prior is about the same as if you just had another 10 years of data of the same sort of size. And again, if anything, it maybe feels a little bit generous. What's a little bit of a shame to me is that when you get to year 11, you don't get any more credibility. So there's no way to get to 10,000 years of data and finally get 100% credibility for your own data. That's it, you're always capped out at 50%. So 50% may be generous, maybe not, we'll talk about that. But I still think it's a bit of a shame that we only stop after 10 years. We never get more than 50%. Okay, but you may remember that a chi-squared distribution is the typical distribution for a standard deviation. So if you have 10 data points, 10 annual data points, and you work out your 95% confidence interval, that 95th percentile confidence interval is going to be somewhere between 70% and 180% of your estimate, which is pretty ginormously wide. In other words, if your estimate was a 10% standard deviation, the true standard deviation might be as low as 7%, great, good news, lucky you, maybe that will come forward in time, or it could be as high as 18%. So you could be gunning for a decrease in your capital requirement based on your own experience, based on your experience being lower than the standard formula, but it's actually quite possible your own experience actually might be much, much higher. And so suddenly that 50% factor doesn't seem quite so conservative anymore. And about an 80% relative error, at least on the upside. Now, it does beg the question, is Warren Buffett successful? Well, no, it doesn't beg that question. Warren Buffett is successful. It begs the question, is Warren Buffett skilled, or is he lucky? Right? You have heard this thing, if there are enough people, enough investors in the world, in a random world, with none having any skill, over the course of many, many years, somebody's going to end up with this phenomenal track record. I don't know that Warren Buffett fits it, but I do worry whether if any of us has had a particularly good period where our claims ratios have been particularly stable, how sure are we that that is actually our own skill and our own underwriting and our own selection and our own discipline in the face of an underwriting cycle, and how much of it is potentially just good luck? It can be quite difficult to know. So the challenge here is that for your own internal purposes, don't be too convinced by your own internal data. And in an application to the regulator, I guess I might expect at least some questions around how confident you are that your estimate is reliable and stable. I have also seen this bite some insurers, where you've applied for your undertaking a specific parameter, you get your credit for lower capital, everyone celebrates, starting to plan for that, but of course that insurer-specific parameter or USP that you derived itself is going to be unstable. When you add more years of data, it's going to be moving around quite a lot more as well. So that might need to be factored into your own risk appetite, that you now have a volatile or variable capital formula on top of your own experience. So there are some give and take elements there as well. So clearly 10 years is not enough to estimate a reliable standard deviation. And I don't know about you, but I don't really feel like waiting around for 50 years before I get something that I can believe. Because as you move into a 50-year period, we have the challenge of, well, how much of the 50 years is still relevant? but it's still quite a concerning graph. I have a very partial suggestion or solution, but still not one that takes us all that very far. And yes, we get a little bit more maths here. So one idea is, well, why can't we use 120 months of data rather than 10 years of data? It's the same time period. If you're just dealing with just hard paid claims, it gets to be quite easy. If you do want to look at what your IBNR and OCR would have been after 1 year, after each of those month ends, it gets a little bit more work. You'd probably have to get way back with some sort of artificial simulated reserving process rather than looking at actual reserves. But you might be able to get monthly loss ratio for 10 years or more. It doesn't give you 120 independent data points though, but at least it does give you something a little bit more. So because we now have a time series, we have a covariance structure or a partial autocorrelate structure, we need to basically adjust this for the time series. So one way might be to just de-seasonalize and then regress on the last 12 or on 12 months, fit some monthly seasonal patterns, or a trigonometric pair. These are basic time series techniques to deal with time series. Or you could fit a Serema model directly. I played around with it a little bit on some data that I did have. You actually get some pretty good results with a pretty limited time series model, where you'd be looking at a one-term autoregressive model, a seasonal autoregressive term, looking back 12 months each time. So you can play around with those until you get a model that you think is actually giving you a relatively decent time series and your diagnostic statistics are looking good. That is going to give you a sensible estimate of monthly residual standard deviation. But now you need to effectively play that model forward to look at what is the annual standard deviation coming out of the model. You can't take that standard deviation and multiply it by the square root of 12 to get you to an annual standard deviation. So you will then have a monthly standard deviation that you can turn into an annual volatility, and that will hopefully have a lower standard error than the naive approach of using 10 annual data points. Now, the effective sample size is probably going to be somewhere between 10 and 120, more likely between 20 and 80. So worst case scenario, you've doubled the effective sample size, so you've significantly decreased your standard error, but depending on what's actually going on inside your models, you may get an effective sample size all the way up to 80, in which case you're finally getting things that are really, really worthwhile. Remember that graph saying that actually so 50 years is enough? Well, if your effective sample size gets to be closer to 80, you're actually doing pretty well. And these are not particularly complicated exercises. The hard work is on the data preparation, making sure you get those reliable monthly standard deviations or monthly closes, monthly loss ratios. You can calculate standard deviations on them quite accurately. Okay, the health warning is because there's no guarantee that even your 10 annual data points aren't a time series. Of course, you don't have 10 independent annual points. You don't even have the credibility that you thought you had. So it probably is worthwhile to look at your 10 annual data points and just check to see what the autocorrelation structure is looking like over there. Okay, so these are the 5 key lessons that I took away from all of this. Portfolio size probably doesn't matter as much as I'd maybe thought. Once you're over 10,000 policies, you're probably okay. Most of the process risk is diversified, and you get reasonable standard deviation and reasonable value at risk results. Again, those niche portfolios may still require some care. Having heterogeneous portfolios maybe isn't as big a deal as I'd worried about. Again, once you're up to 10,000 and certainly up to 100,000, really most of that disappears. The bigger thing there is just to think about surplus. Surplus is relevant for those smaller portfolios, but for larger portfolios, where typically maybe not going to be used anyway, isn't such a big deal. But the 2 most important things to me is that coefficient of variation matters far, far, far more than your loss ratio or your standard deviation alone. You're obviously going to be looking at the standard deviation, but if you haven't got a handle on your coefficient of variation, you may well be misunderstanding your portfolios. And all the challenges we had around estimating standard deviation are only going to apply with your coefficient of variation as well. I did look at some techniques of trying to have non-parametric ways of fitting the value at risk using Cornish-Fisher approximations. Those work sometimes, but the same estimates you need to get for skewness and kurtosis are subject to the same challenges around standard error that we have for standard deviation. It's still not quite a good fit. So coefficient of variation really, really crucial. And then finally, as I said, 10 years data is probably not enough. So you want to either make the most of the data you have using monthly data and time series approaches, or look at FSI 4, attachment 7, the method 3, where you actually are given the road to use a individual claim frequency and severity model. You build it up from the ground up, as I've done, and you've got a lot richer data, a lot more work that may well be able to give you a more reliable approach. Interestingly, of those 3 methods that Sam gives you to apply for an ISP, only one of them is used in Solvency II. Those 3 methods are somewhat complicated. They're not entirely consistent. They also require you to make stronger statements around various assumptions, again, where it's very difficult to test them. And it looks to me like those are really more taken out of the overall calibration work that EOPA did kind of 15 years ago or so. There's a fair amount of work to be done there. Okay, we haven't had any burning questions. I do hope there are a couple of questions, and that's where I'm going to leave it otherwise. Thank you. Not yet.
Hello.
There we go.
Thanks, David, for the presentation. I think everyone's a bit scared to ask questions, but I fully agree with what you started with. Is that like we need guidance on how to approach the standard formula appropriateness question. It's not a simple matter. From a sort of reflecting on myself, we've kicked a qualitative approach down the road for many, many years already, some kind of a, approach to qualitatively validate why the standard formula is appropriate for us. But if you really want to do this, something like what you have presented today is necessary. So I guess my question is, we have gone down the route of ISP modeling, very early stages, just to get some kind of a sense for, can we produce our own factors, for lack of a better word. Our data is woeful, so I mean, we have a long, long way to go. But I guess what I'm trying to get to is, I think the industry needs guidance on how to approach this, and isn't what you have presented here today maybe the start of that, and how do we take this further? Because I agree with you, the regulator's going to start knocking on our doors to answer these questions, and I don't think they are going to give the guidance to us.
Thanks. Yeah, I mean, the short answer is often to start, as sounds like you have been doing as well, because until you actually start trying to gather the data to try to do the calculations, you don't even know exactly what form of data you need and how it works. I think this does actually provide a relatively straightforward, despite the pain that I had to go through to try to get fake data. Hopefully you need real data, not fake data for your applications. So organizing the data perhaps is a challenge, but at least you're working with what you have. Looking at the standard deviation, looking at the means, looking at the coefficient of variation, looking at the monthly and annual data is a relatively straightforward process. We have seen relatively slow progress from the regulator around coming out with guidance notes on some areas. In theory, there has been noise around looking at an overall recalibration. We're going to be chatting to the Prudential Authority in a few weeks to understand their energy and appetite for that, because an industry-wide exercise to recalibrate is also interesting. It's not the same as an insurer-specific process. Those are both things that could be useful. It has been quite a while since the original calibration. As you probably know, I am involved in the so-called SAM Phase 2 subcommittee, which has put out the odd guidance note and information notes. That's been like a lot of hard work these days, so I don't know if I necessarily want to be putting up my hands to volunteer for another one. But I have some colleagues in the audience who have been finishing off some recent ones, so maybe they'll be looking for a new challenge. So my suggestion is, yes, get started with various steps. Hopefully a couple of these ideas will just prompt some thoughts in your mind around some initial early steps. Not yet.
Cool. Thanks, David. 2 questions. One may be easier than the other, and I'll let you pick which one.
I'm just taking the first one, thanks.
Cool. Didn't say I'll say them in order. One is, when you showed the effect of decreasing the loss ratio from 65 to 25%. You only showed it for 1,000 and 100,000. What happened in between? What happens at the million? And then the second question, the lack of convergence, could that be a function of normal and log normal distribution? And have you looked at any other distributions and how they affect this?
So the sad story is what happened. Well, the two things what happens. The one is it was gremlins in the calibration process, because the calibration process is incredibly painful. But the results that I have no reason to expect that you aren't going to get a consistent message across that, right? As you increase above about 100,000 policies, very little of any exciting things happen. All the specific risk has disappeared. We're just left with a systematic component. So I don't think there's too much that's exciting there. I did play around early on with a negative binomial and gamma. Again, results really don't look that different. You end up with slightly different skewness, slightly different kurtosis, but the basic messages are the same. I alluded to very briefly the idea of looking at Cornish-Fisher approximations to try to specify those variant risk numbers without having to assume a distribution at all. But for the most part, those are actually more fragile than having to assume a stronger distribution. I thought that log normal would be a less good fit in general, because how could it possibly fit that well? But I was actually surprised that it does fit reasonably well for the sorts of portfolios we're coming out of that. And I don't think it is just because I had a log normal severity within that, because it is a compound process rather than just an individual one. I'm going to be continuing this though to see what more can come out of it. But I think the broad messages are the same. The coefficient of variance really, really matters, and that's the be all and end all. The thing about the coefficient of variation though, is that I fairly mechanically just decreased the loss ratio and left the standard deviation where it is. And actually I think one of the reasons my calibration was struggling is that it might have been quite hard to actually get that high coefficient of variation to actually to exist. So probably needs to aim for slightly less extreme results there to show that yes, elevated coefficient of variation gives you elevated value risk over standard deviation rather than the extremes. That's probably the lesson for me there as well.
Hi, David. Quick one. So one of the big assumptions in the calibration is the expenses follows claims. What's your thoughts on the appropriateness of that, especially given that the standard formula allows you to take the benefit of quota share benefits against the entire premium reserve risk, and most reinsurance contracts actually will not let the insurer pass the expense risk onto the insurer. Is that not a fundamental problem?
It's a problem. I don't know whether it's fundamental. It really does come at least partly into what we're counting in as expenses. Because for the most part, operational expenses should be volatility dampening. But if you do start looking at profit commission and there's other creatures come into there, then I think you have a concern. My preference is that those items are modeled explicitly and directly. And again, we've got working groups looking at those rather than muddying the waters there. What Sam has done is completely consistent with Solvency II there as well. I think they did some initial testing to see that it didn't have a major impact. So I think there is a challenge if you're going to assess your own appropriateness of the standard formula, if you had concerns around that due to business model, operating model, and so on, that is something you would want to plug in there. But I'd be surprised, frankly, if that was something that the regulator was going to kick particularly hard.